The word of the day is polyatomic ion. Poly is Greek for many. I'm hoping you know what an atom is by now. An ion is something with a charge. Here's a classic example. You've heard of sulfate. You've used it in a lab many times. What is it? It's a polyatomic ion. It is constructed of one sulfur, this yellow one is a sulfur, and 4 oxygen atoms. I'm hoping this makes sense to you. When we write SO4, 4 oxygens, 1 sulfur. The weird thing is that it has a -2 charge for the whole thing. Not for each individual atom, but for the whole thing. So you need to conceptually think of this as just one ion. It's a -2. You really don't need to look inside it. The only time we'll look inside is when we say, well, how much does that thing weigh? Other than that, we just treat it as an ion. So if we use this in a salt, in a formula, if we had a metal ion that was a +2, I just put M here, it could be zinc, copper, magnesium, calcium, there are lots of +2 ions. But you would see that this balances +2, -2, just one of each is all we need. If, on the other hand, we had a sodium ion with a sulfate ion, this is not in balance. This is only a +1, that's a -2. We'd need a second sodium to make sodium sulfate. 2 sodiums for every sulfate. So here's an example of a formula written with a polyatomic ion. Sulfate is SO4. You see 2 sodium ions, that's why I wrote Na2. And the sulfate is SO4 with a -2 charge, sodium sulfate. Here's an IC 2020 simulation to illustrate the idea of a polyatomic ion. I'm hoping you see this is sodium sulfate, the same as we saw with the tennis balls. And as I start this up, the water can dissolve the salt. And as you can see, the sulfate is not splitting into 5 separate things. It's just one thing. It's one big ion. And that's the way, and that's the purpose of polyatomic ions, is for you to think, yeah, it's many atoms, but it's one thing. And so we call it sulfate, and we see it bounces around just like these sodium ions do. They're only one atom. This is 5 atoms. So here on the back of your periodic table is where you find polyatomic ions. They are here. So the simplest one is hydroxide. It has only 2 atoms, 1 oxygen, 1 hydrogen right here. The one we've seen in the model is this one, sulfate, SO4, so 1 sulfur, 4 oxygens. You can see a common ending is this ATE. So when you see that, think polyatomic, look on the back of your periodic table. The other thing this page is useful for is the transition metals. Transition metals, you can't tell their charge from the front of the periodic table, but here's silver, copper, zinc, iron. Iron has 2 forms, so you need to be more specific about that. Nickel. So this can help you when you're saying, what's the charge of? Look for it here if it's a transition metal. So transition metals are these in the middle. And you can see that, there some of the columns had designations on the top. And we use those in assignment 1 to figure out the formulas of ionic compounds. But these are less predictable, these transition metals. So you can't tell just by looking at them what their charges will be. That's when you look on the back of your periodic table to figure out what they should be. So here we go. We're drawing the pictures. We're writing the formula. We've already got the name. So the first one is the one I just showed you with the tennis balls and the wiffle ball. So there's 2 sodiums for every sulfate. There's the polyatomic right there. It acts as one thing. Let's look at the next one. We have 2 names, lithium and phosphate. It is essential that you find these on your periodic table, otherwise you'll be guessing. So find lithium, that's an element. So you'll find it on the periodic table. This is not an element, this is a polyatomic. It's on the back of the periodic table. So it's one thing, but it has many atoms inside it. Look first. I'll show you the answer after you've looked. So here is phosphate. That is like sulfate. It's 5 atoms. Charge is -3. Lithium, on the other hand, just Li, it's 1 atom. Charge is +1 if you read your periodic table correctly. So I'm hoping you see then, it's not 1 lithium, it's not 2 lithiums. That's an ugly circle, but you get the idea. 3 lithiums for 1 phosphate. That makes the charges equal. For every plus there's a minus. And the way you write that as a formula is Li3, PO4. Okay, now we're on C. Again, 2 names. The first name is a metal ion, calcium. The second name is a polyatomic. This one is going to be a little trickier than the ones we've done before. Again, you need to use your periodic table first. What are the charges? Now, when you see the word nitrate, you might be tempted to think, okay, nitrogen, which is not correct. This nitrogen ion with a -3 charge, that's nitride, not nitrate. To find nitrate, you need to look at the back of your periodic table. It's a polyatomic ion. So here you can see when it ends with ATE, it's polyatomic. So if you read it correctly, nitrate is NO3, all one thing. Charge is -1. That's what it says right here. Calcium is a +2 ion. Nitrate may be a little hard for you to read. It is NO3. The charge is -1. I'll specify this time and say it's -1. You should see we have an imbalance in charges. We have +2 and only -1. We need another minus. That means we get another nitrate ion. There it is. That's a good picture for calcium nitrate. 1 calcium ion, 2 nitrate ions. Now the challenge is, how do you write that? 1 calcium. This is nitrate, and there are 2 of them. If I just wrote a 2 here, it looks like 32, so that's no good. If I put a 2 in the middle, that's no good either. So the way you do this correctly, parentheses around the polyatomic. It's a group. There it is. It's a group. You can see it. Put a parentheses to say it's a group, and then put the 2 outside the parentheses. This equals the picture. 1 calcium, 2 nitrates. Need the parentheses to do it right. Okay, so now let's look at D. It's silver. That's a transition metal. We'll find it on the back of the periodic table. It's carbonate. Anything that ends with ATE is polyatomic. Find the charges. Look at your periodic table. Find the charges first. Can't do it right if you don't find the charges. All right, now silver is Ag from the Latin, argentum. It's a +1. Carbonate is a polyatomic. Making a nice big circle so I can fit all the letters inside. Charge is -2. Therefore need one more silver. Now I have equal numbers of pluses and minuses, +2 and -2. So I write what I see as a formula. Ag, 2 of them, CO3 as a group. I don't need any parentheses. I only need parentheses in the previous example because there were 2 of the group. Here, there's only 1 of the group. If I don't write anything more, it's done. No parentheses required. Last example, zinc hydroxide. Find them on your periodic table. In this case, hydroxide is polyatomic. It's odd that it does not end with ATE, but it is still a polyatomic ion, so you have to find it on the back of the periodic table. Find the charges. Zn is a +2 ion, zinc. Hydroxide is OH. That's 2 atoms, oxygen and hydrogen. Charge is -1. So that means I do need a second OH so that I have 2 negatives to go with the 2 positives. Formula. It's 1 zinc and it's 2 hydroxides. So this is hydroxide, it's OH. If you put a 2 here, it only refers to the hydrogen, not the oxygen. But you should see in the picture we have 2 oxygens, 1, 2. Therefore, I need to not write just OH2. Correct way is to say OH is a group. Parentheses 2. Now the 2 applies to everything inside the parentheses, just like in math. And now it is correct, 2 hydrogens and 2 oxygens. That's the formula for zinc hydroxide. Here's the last question on my instruction. Strontium nitrate. So, find it on your periodic table. Strontium is Sr. Charge is +2. Nitrate we've seen before. Polyatomic. -1 is its charge. So you should see that this is not in balance yet. Need a second negative charge. That means a second nitrate. So this is the picture.
The ionic bonding looks like this. Now, we get to think about how do you write that as a formula?
If you understood what I said earlier, nitrate is a polyatomic. You can write it in the parentheses and then say how many are there? I see 2. So that's a formula for strontium nitrate. And you can see that's right here. But how about this? Maybe this is equivalent. Is it equal? All right, so if I write that, SrNO6. This is not the same as the one before, so it's not equal to, because this 6 only multiplies the oxygen, not the nitrogen. And just as we saw earlier with the zinc hydroxide, there are more than one nitrogen here. So this is one nitrogen and 6 oxygens. And that's not what we have in the picture. We have 2 nitrogens and 6 oxygens. So you could conceivably do this. It's true, but it's less informative than this. But correctly translated mathematically, this that I've just written here, it is true, but this is not true.